The magnetic field. Our planet is cocooned in an invisible shield, a magnetic field that extends far into space. Generated by the swirling motion of molten iron within Earth's outer core, this geodynamo creates a force field that protects us from harmful solar winds and cosmic radiation. This magnetic envelope not only plays a crucial role in preserving our atmosphere, but also guides migrating animals and influences navigation systems. In essence, the magnetic field is both a guardian and a guide, integral to life on Earth. A weakening shield. Despite its robustness, the Earth's magnetic field is not a static force. Recent observations have revealed a gradual but noticeable weakening in certain regions, giving rise to what scientists describe as a hole in the shield. The most prominent example is the South Atlantic Anomaly, SAA, an area where the field's intensity is significantly reduced. This weakening isn't merely a scientific curiosity. It has practical implications. With a diminished magnetic shield, high-energy particles from space can penetrate closer to Earth's surface, posing risks to satellites, astronauts, and even affecting power grids on rare occasions. This segment sets the stage for understanding how such a weakening shield can impact modern technology and our daily lives. Navigating the SAA. The South Atlantic Anomaly stands as a region of intense focus for scientists and engineers alike. Essentially, the SAA is where the inner Van Allen radiation belt comes unusually close to Earth, resulting in a spike in radiation levels. This hole in the magnetic field forces spacecraft to navigate a more hazardous environment. Satellites passing through this area are exposed to higher doses of radiation, which can disrupt onboard electronics, cause data corruption, or even shorten the lifespan of sensitive instruments. To mitigate these risks, mission planners incorporate specific orbital strategies, enhanced shielding, and operational protocols designed to protect vital systems during transit. Navigating the SAA is a vivid example of how natural phenomena compel technological innovation and adaptive planning. Unraveling the causes. The phenomenon of a weakening magnetic field and the resulting anomaly raises important scientific questions. At the heart of the matter is the geodynamo, the process by which convective currents in the liquid iron of Earth's outer core generate magnetic forces. Fluctuations within this turbulent system can cause regional variations in field strength. Moreover, interactions between the core and the overlying mantle may further influence these changes, potentially creating transient holes, such as the SAA. Some researchers speculate that these localized weak spots might be early indicators of a broader, long-term shift in Earth's magnetic configuration, possibly even hinting at an eventual geomagnetic reversal. Understanding these causes is key to predicting future behavior and preparing for the consequences of an evolving magnetic field. The SAA in history. The South Atlantic Anomaly is not a recent development. Its presence has been documented for decades. Historical measurements, initially taken with ground-based instruments and later refined with satellite data, have shown that the SAA has been changing over time. In the mid-20th century, scientists first noted unusual radiation levels over the South Atlantic region, and subsequent observations have confirmed that this anomaly is both persistent and dynamic. Historical records reveal fluctuations in the size and intensity of the SAA, suggesting that the anomaly is tied to the cyclical nature of the geodynamo. By studying its past behavior, researchers can glean insights into the processes driving these changes and better forecast what might lie ahead. Monitoring and research today. A suite of advanced monitoring systems is dedicated to tracking the Earth's magnetic field. Satellite missions, notably the European Space Agency's Swarm constellation, provide high-resolution, real-time data that map the magnetic field's intricate details. These observations are complemented by a network of ground-based observatories and sophisticated computational models that together create a comprehensive picture of magnetic variations. Continuous monitoring is essential, not only for advancing our theoretical understanding, but also for the practical management of risks associated with radiation exposure in space. This concerted research effort allows scientists to observe subtle shifts, track the evolving boundaries of anomalies like the SAA, and develop predictive models that can inform everything from satellite design to power grid management. Tracking the divide. One of the most intriguing challenges in studying Earth's magnetic field is tracking the boundary between regions of strong and weak intensity. This dynamic divide is where the robust magnetic shield meets the areas of vulnerability, such as the SAA. By closely monitoring these transitions, researchers can gain valuable insights into the internal processes of our planet. The shifting boundary is not only a marker of the current state of the magnetic field, but also a potential precursor to larger-scale phenomena, such as a geomagnetic reversal. Understanding how and why this divide moves over time helps scientists refine their models of Earth's interior and enhances our ability to forecast future changes, with significant implications for both science and technology. Predictions and concerns. Looking ahead, the future behavior of Earth's magnetic field remains a subject of both scientific inquiry and public concern. While some experts suggest that the current weakening in regions like the South Atlantic anomaly may be a temporary fluctuation, others warn that it could be indicative of more dramatic shifts. One possibility is a geomagnetic reversal, a process where the north and south magnetic poles swap places, a phenomenon that has occurred several times in Earth's history. Although such reversals unfold over thousands of years and are not expected to cause immediate catastrophic effects, they could disrupt satellite operations, communication systems, and navigation networks during the transitional phase. This segment delves into these predictions and concerns, emphasizing the importance of preparedness and robust scientific research to mitigate potential impacts. The importance of understanding. In wrapping up our exploration, it's clear that Earth's magnetic field is far more than a static, unchanging barrier. It is a dynamic and evolving shield whose fluctuations have profound implications for technology, space exploration, and our understanding of the planet's inner workings. The hole in the magnetic field, exemplified by the South Atlantic anomaly, serves as a reminder of the complex and sometimes unpredictable nature of our planet. By investing in continuous research, advanced monitoring, and adaptive engineering solutions, we can better anticipate changes and safeguard both our technological infrastructure and our way of life. Ultimately, understanding these magnetic shifts is not just an academic exercise, it is a practical necessity for navigating the challenges of an increasingly interconnected and technologically dependent world.